In last video, you have seen about dimensions and dimensional analysis. Dimensions of physical quantity are the powers to which fundamental units must be raised in order to obtain unit of given physical quantity. And dimensional equation is an expression which gives the relation between derived units and fundamental units in terms of dimensions is called as dimensional equation or dimensional formula. This dimensional formula is expressed by square bracket and there is comma not written between any two symbols. Today we see uses of dimensional analysis. There are three uses of dimensional analysis. First use is to check the correctness of physical equation. Second use is to determine the conversion factor between the units of same physical quantity in two different systems of units. Third use is to establish the relation between related physical quantities. See the uses of dimensional analysis. First use is to check the correctness of physical equation. Second use is to determine the conversion factor between the units of same physical quantity in two different systems of units. Third use is to establish the relation between related physical quantities. With the help of dimensional analysis, we illustrate these examples of physical quantities. So first use is the to check the correctness of physical equation. In any equation is related with different physical quantities. If the dimensions of all the terms in both sides of equations are same, then that equation is dimensionally correct. This is called the principle of homogeneity dimensions. You know about the kinematical equations of motion. So consider first kinematical equation of motion, that is V equal to U plus AT, where V is the final velocity, U is the initial velocity of particle, A is the acceleration of the particle, and T is the time. By using dimensional analysis, first we obtain the dimensions of velocity. So velocity means rate of change of displacement with respect to time. So dimensional formula, velocity equal to displacement divided by time, means displacement is denoted by letter capital L and time is denoted by letter capital T. Is written in square bracket. So the dimensional formula for velocity becomes square bracket V equal to 1 in length, 0 in mass, and minus 1 in time. So these are the dimensions of final velocity. So this is the dimensions of left hand side. Now we obtain the dimensions of initial velocity. These are same as that of final velocity. So dimensions of initial velocity is denoted by letter U. So square bracket U equal to 1 in length, 0 in mass, and minus 1 in time. Then third term at RHS side is AT. So this can written like this, square bracket A into square bracket T. Then knowing the dimensions of acceleration, we can write the dimensions of acceleration here. 1 in length, 0 in mass, and -2 in time. Then dimensions of time are 0 in length, 0 in mass, and 1 in time. When we simplifying it, we get the dimensions of the term ET as 1 in length, 0 in mass. This is here at power of time is -2. Here is +1. So this becomes -1 in time. Suppose LHS side, the dimensions of velocity v are 1 in length, 0 in mass, and -1 in time. Suppose this equation number 1. Dimensions of initial velocity on RHS side, 1 in length, 0 in mass, and -1 in time. Suppose this equation number 2. Then dimensions of third term at RHS side, 80. This is 1 in length, 0 in mass, and -1 in time. This is equation number 3. From equation 1, 2, and 3, we can write the dimensions of left hand side and RHS side are same. Thus, we can prove the physical equation V equal to U plus AT, and the dimensions of all the terms on both sides of the equations are same. Hence, V equal to U plus AT, this equation is dimensionally correct. Now, second example is the kinematical equation of motion. So second kinematical equation of motion is S equal to ut plus half at square, where S is the displacement of the particle in time t, U is the initial velocity of the particle, t is the time, A is the acceleration of the particle. Now left hand side, dimensions of displacement are, that is square bracket S equal to 1 in length, 0 in mass, and 0 in time. So LHS dimensions, one in of displacement, one in length, 0 in mass and 0 in time. Then right hand side the terms are ut plus half at square. First we write the dimensions of ut. So this can written like this, square bracket u into square bracket t. Then writing the dimensions of initial velocity, 1 in length, 0 in mass and minus 1 in time. Then write the dimensions of time, 0 in length, 0 in mass and 1 in time. Then taking simplification, we get the dimensions of ut as 1 in length, 0 in mass and 0 in time. Then third term is half at square on RHS side. This half is the number, it has no dimensions, and the dimensions of a into t square. So this can written like this, a means acceleration and t square means time. Then writing the dimensions of acceleration and dimensions of time, taking its square and simplifying, we get 1 in length, 0 in mass and 0 in time. So these are the dimensions of all the terms on right hand side. That is, ut dimensions are 1 in length, 0 in mass, 0 in time. Half, it is the number, it is dimensionless, and the dimensions of at square are 1 in length, 0 in mass and 0 in time. So dimensions on of all the terms on LHS side and right hand side are the same, hence the equation S equal to ut plus half at square is dimensionally correct. Today's homework, check the physical equation v square equal to u square plus twice as is dimensionally correct. Also, second example, the period of simple pendulum is given by capital T equal to 2 pi into root of L divided by G, where L is the length of the pendulum and G is the acceleration due to gravity. Prove this relation is dimensionally correct or not. Second question is state the uses of dimensional analysis.